how we read a mass spectrum. They are at the same time pretty simple and pretty complicated. And my cartoonish versions of a mass spectrum aren't going to look quite like a real one. Definitely do yourself a favor and look up um, a mass spectrum for a simple hydrocarbon or look at examples in the book. It'll give you a little more of a detailed picture. We'll talk about some of those details and some basics in reading these spectrum. So mass spectrum for a small molecule could look something like this. Probably a lot more small minor peaks here and there. If you get a real spectrum from the spectrometer in lab, you might see a lot more complication here. But this is a simple representation of one. So our molecule here is molecular weight is 72 grams per mole. The X scale is mass to charge ratio. Since the charge of all the particles we see is generally all +1, then essentially you have an X scale that's mass of the molecule and the particles, right? So we're looking at pieces and masses, and the Y scale is abundance. So if we have a really small peak or a really tall peak, this is the mass of the fragment that made that peak, and then the height of it is how many of those pieces were there. So this molecule came apart, it fragmented within a device, and all of its little pieces were detected. The most common one was that mass to charge ratio of 43, so an atomic mass of 43. That's our most common particle. Two terms we use for looking at things on the spectrum is one is base peak. Not always a really particularly useful piece of information, but it's just whatever peak is the tallest. Right. The other one is the molecular ion peak. So if we know what our molecule is, in this case its molecular mass is 72 grams per mole, then the molecular ion should have the same mass. And oftentimes the largest mass peak on the spectrum, not the tallest, but the heaviest peak is your molecular ion. Not always, though. It can be a little bit tricky. So two things. The molecular ion can sometimes be the base peak for a really stable molecule like benzene. A lot of times it doesn't fragment that much. So the most abundant peak can be something like the molecular ion itself. And sometimes you don't see it. That's the hardest part about mass spectrometry is for a molecule that fragments easily, occasionally the molecular ion peak can be all but invisible. So a problem you won't so much run into with theoretical and textbook spectra, but a problem you will run into with real spectrum sometimes is you don't always have an obvious heaviest peak. Mass spectrometry can be really good at identifying molecules in a quick and simple way by looking for the molecular ion peak, because then say you have an unknown, then you have the complete molecular mass of that unknown, which is really, really powerful, right? And if you figured out the molecular mass of a compound, that limits it to a very few things, and then we can look at the details either by comparing spectrum to known spectrum or looking at fragmentation patterns and what we might expect for something like a hydrocarbon, and you can actually figure out unknowns from there. The vast majority of chemists in a quick way will match spectrum to known, but there's a ton of detail we can get out of these. So reading a mass spectrometry, the tallest peak is the base peak. Molecular ion is arguably the most important one, which should be the heaviest peak, though of course there can be some complications there. For simple hydrocarbons and for a lot of spectra in general, you'll see a lot of other peaks. So say there's a really small peak here. That's going to be at 73. Does that mean the molecular mass of my compound is really 73 because I got this little tiny thing here? Probably not. So one of the things to keep an eye out for and look for in mass spectrometry is a lot of times you'll see these small peaks ahead of the larger ones where we kind of expect. And we call those M+1 peaks. And those come about from the sensitivity of the device detecting isotopes of atoms, right? So one in every 100 carbon molecule, not chlorine, one in every 100 carbon is carbon 13 instead of carbon 12, right? So 99% of everything we see is that. 1% is carbon 13. But again, a drop of solution is going to give us, billions of atoms. So even though it's only 1%, the machine can detect that, and so you'll see these small peaks there. Not necessarily a lot you can do with that information, but it's definitely something to keep an eye on. So if you're looking at this and you're like, all right, what compound do I have here? These little tiny fractional peaks. For carbon-13, they're going to show up very small, and we don't want to confuse those with the molecular ion if you're trying to figure out what's going on. Another thing that can be useful in reading spectrum is kind of coming up with sort of simple shortcuts. So if you have a spectrum, right, this one's got a lot of peaks. Right, I've labeled 15 and 29. Notice there's sort of a regularity here in the gaps in between each major peak, right? And so, of course, you're probably in a real spectrum going to see other peaks show up here and there. Either from additional fragmentation, smaller peaks, or n+1 peaks, a little bit larger. And you kind of have to learn to live with those and kind of understand when they're important and when they're not. But if this peak's at 15, right, that is more than likely CH3+, right? So 1 carbon, 3 hydrogens, carbon's 12, hydrogen, 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 another 1, 1, 1, 12, 13, 14, 15, right? So we're looking at CH3 as our fragment here. And 29 is 14 more than 15, right? So how do you get to 29? Right, you start with your 15 from CH3, add a CH2, right? 12 from carbon, 13, 14, right? You've added 14 to get to 29. What's the next peak there? 43, right? That's another 14, right? Essentially you're going plus 14, plus 14, plus 14, plus 14. If we see that kind of pattern, these regular small gaps of 14 atomic mass, what you're probably looking at is a hydrocarbon, and you can, without spending a ton of time trying to figure out a starting point here, you can say, okay, well, this peak shows me I got 1 carbon, 2 carbons, 3, 4, 5, 6, 7, 8 carbons. And hey, maybe this is octane. Right? And then that's a starting point. Say, okay, 1, 2, 3, 4, 5, 6, 7, 8 carbons. Maybe there's another peak out here. So there's a chlorine on the atom and such. So of course you still want to look at the molecular ion and think about molecular weights of the compounds. But if you see these very regular patterns, it can help you find that hydrocarbon structure. And that can be the whole molecule, or it could just be part of it. But it tends to have this distinctive pattern, and they tend to kind of peak and come back down. The smallest and largest fragments can be really hard to see, be very, very small peaks. But if you're just trying to take a quick look and think about what could this molecule be, that's an important thing to look at. When you start seeing different gaps, so a gap that's more than 12, more like 30 and things like that, and then you got to be thinking there's probably some other atom involved. Maybe there's a halogen or an oxygen or something different going on that's breaking up our simple plus 12 pattern there. But that's just a starting point. The more you look at these, the easier it will be. But it just takes practice to think about, all right, well, okay, is this important, or is that an n+1 peak? And what could these fragments be, right? And hydrocarbons tend to be the easiest ones to look at.